Hello students, welcome to lecture 7. In this lecture, we will introduce a new linear method called linear regression that can be used for regression problems as well as useful in the classification problems. Before moving on, let's briefly review the previous lecture in which we introduced noise, possible noise in the generated data, or even the target function can be noisy. And we also reviewed a very few examples of error function. And now also we mentioned that our target function is now a target distribution that incorporates possible noise in the data, both in X and Y. And also we have said that the error function should be designed based on the application. For example, the error for CIA entrance applications that use fingerprints should be different than for supermarket that issues a discount. So we talked about false positive, false negatives that needs to be penalized when designing an error function. So in today's lecture, we will study more about the linear regression. First, we define linear regression problem and we discuss about the algorithm that can be used for linear regression. And then we discuss about a possible use for solving binary classification tasks. Let's revisit our credit card or credit application approval problem that we considered in when we studied perceptron learning algorithm. There, we were interested in binary answers. Approve credit or deny credit, given the applicant applying for credit card. But now, let's ask a different question. Given this information, okay, one applicant wants to get a credit card. So you say, okay, I approve. But next question is how much? What could be the credit limit for this applicant? This is another problem. Credit limit can range from 0 to 100,000, 1 million. Now the task is to find this unknown target function, which is the ideal credit limit formula. Given data, and then the y here can range any real valid number. So it could be 1 up to 10,000, 500, or even more. All other components of our learning flow remain same. We'll be given training examples, x for example, and then y here constitute not plus minus 1, but some real valued number. The learning model, the algorithm with a hypothesis set, and task is to estimate our G for these kind of regression problem. Let's take a look at the formation of the linear regression hypothesis. For that, we consider the following information from one potential or possible applicant applying for credit card with the following attributes. We have age, gender, annual salary, year in residence, year in job, and current debt. What we do is next, we take these features and then form a vector that contains the features of a customer. X1 could correspond to age, X2 to gender, X3 to salary, X4 year in residence, X5 year in job, X6 current debt, and any other additional features of the applicant can be used in forming the feature vector. And here x0 is the artificial coordinate that we introduced for our convenience, which is coupled with w0, right? So now the task is, for the given feature of customer, our goal is to approximate the desired limit. Desired credit limit. Is it 5,000, 10,000, or more or less? I can write it down here specifically. Let me write this feature as x1, x2, x3, x4, x5, x6. These are the vector that corresponds to this attribute of the applicant. And we also have here x0, which is always 1 always. And now finding the desired credit limit is equivalent to finding the optimal weight combinations. Okay, that will approximate to our desired y. Okay, so what we can do here, so w0, w1, w2, weight, okay, 3, 4, 5, 6. So each feature is combined with different weights. The current debt can be associated with a negative weight. So WC could be a negative weight value, while annual salary can be given a much positive. The linear regression hypothesis will consist of the following class of functions, h of x equal to w transpose x. So it very much looks like a perceptron, but in the perceptron case we had a sign, which will define whether this weighted sum is positive or negative output, which could be plus minus 1, right? But in this case, we are trying to learn the weight of this linear hypothesis, linear regression hypothesis, that will give us the real valued output. The linear regression problem here is a supervised learning problem, which means that for every given point or applicant, we have corresponding y which represent the desired credit limit. You may wonder where y comes from. Bank collects information from hundreds or thousands of applicants, and bank specialists will review all these applicants and provide desired credit limit for each applicant. For example, given the following information from one of the applicants, the bank specialist may decide to give desired credit limit as 5,000. Then our y is 5,000. Our task is to find the appropriate weights or the optimal weight combination that will approximate the 5,000. Like in the perceptron, we want to learn these weights. Illustration of the linear regression problems for one-dimensional input, x, which is a scalar value, and for the example which has two features, x1 and x2, and then y. In classification problem, we are basically interested in separating good from bad, or finding decision boundaries that separates two class of input data set. And assume that we have data from 9 applicants, which is shown here. For example, for the first applicant, let's call it as x1, and then desired y1. Okay, so this will be x1, y1. Here, all these data points represent the desired y, the desired credit limit, which is provided by the bank. Now our task is to find this linear function that will give minimum difference, minimum error between desired and then estimated. Across all data from 10 applicants, we can assume this feature as depth. As the depth goes higher, then desired credit limits go down. Our task is finding these hyperplanes with small errors. So error can be calculated based on this. This is desired, okay, and what we obtain here is predict. So we want to minimize this error for all possible examples. Here we don't have error 0, small residuals. What happens if you have two different features? Let's assume that x1 is salary, x2 is debt, y is given desired limit. Then in 2 dimension we are interested in finding this hyperplane, 2-dimensional hyperplane, which will again give us a minimum small residual between y and then y hat predicted given 2 different features. For regression problem, we use the following squared error function or squared error measure to approximate the desired credit limit. It's a function of y hat and y, and simply the difference between 2 squared, right? We call it as squared error. Y hat is the following. Right? So in sample error will be represented as follows. In sample of given hypothesis, which is represented by weight and average across n examples and training points, summed across all individual points. Okay, these are the point-wise error measure. Then we can get the in sample error. Well, out of sample error will be similarly using the squared error function or measure, where we have the expectation over the possible y and then x, right? But in out of sample error, because we don't know the future y, it's not easy to calculate. Now next question is, how can we minimize this in sample error? In perceptron case, what have we done? The perceptron in sample error was minimized by trying different combination of weights and then using a simple weight update rule. They are also based on point-wise error measure. Let's take a look at this quiz. So consider using linear regression hypothesis, which is given in the following form, to predict the credit limit of customers, represented by vector x. Which feature below shall have a positive weight in a good hypothesis for the task? Well, here we have birth months, feature of the customer or applicant, monthly income, current debt, or number of credit cards owned. So we are interested in the positive weight. Surely, or we can think that the positive weight should be given to monthly income. The more income, the higher positive weight. Okay, so customers with higher income should naturally be given a higher credit limit, which is captured by the positive weight on the monthly income feature. So let's go back to the question we just asked before the quiz. How can we minimize the in-sample error for the regression problem? We said that the in-sample error is basically pointwise averaged sum of the squared error, as shown here. So what we have here inside the error function is the inner product. This is a dot product between our example and then the given weight minus y. So first, let's derive the matrix form of this in-sample error and then talk about the possible minimization of it. We do some simple rearrangement for convenience. This is in the product. We can switch the order of the weight, the given example, due to the conjugate symmetry property of the inner product or dot product. This is our first step. This is the scalar normalizer or averaging operator. We can write this sum as the following. This is the norm. The following sum can be written as follows, where each element of this norm is a scalar value after this abstraction, right? In a product gives us scalar minus desired credit limit, another scalar. So we have now n-dimensional vector, norm of n-dimensional vector, which is equivalent to the following. We need to do one more change here. If you take a look at this location of the examples, n examples, right? And the weights applied to each of them, what we can do is that we can rewrite them as x1 in the product between x1 and then weight, x2 and weight, and xn as a weight. By doing that, we are forming a matrix X which contains our data. This is the vector or example from one customer, one applicant, up to n. Each is in the product between this vector and then weight. Weight is a tall vector. And we have y rearranged as another tall vector. This is equivalent form. This allows us, in turn, finally, to write our inner product in the following matrix form, where we have input data, which has the following dimensionality, n times d plus 1. N corresponds to a number of different examples, number of points. D is the dimensionality of the feature vector for each applicant. What is 1? Can you guess? That is our artificial coordinate we introduced. And we have the W, which is of the following dimensionality, d plus 1. Each feature vector is weighted with weight vector. We also have the Y as a tall vector. Each entries of this vector correspond to the label given. They are usually, again, a real valued number, integer. Now, given the following matrix form of the in-sample error, our next task is to minimize it. All right, here. So we want to find the weight that will minimize our in-sample error. This is the matrix form of the in-sample error for the regression that was obtained from the mean squared error function. Let's talk about some properties of this in-sample error function. We can see, because it's norm, okay, squared, it is a continuous and it can be differentiated. So it is differentiable function. It's also a convex function. So the convex functions are very convenient ones to work with. They come graphically in the following form. Okay, assume this is our in-sample error. Convex function will only have one minimum. Okay, one global minimum as compared to other types of function that may be in the following form. If our error function is the following form, then it's not a convex function because we have different possible minimum points. Let me erase this. Our task is to find the weight that will provide us the minimum of this in-sample error, right? For that, we can consider the necessary conditions of the best possible weight, where we deal with the gradient of in-sample error function. Okay, so the gradient of in-sample should be 0. These are the values, the tall vectors. So gradient of in-sample with respect to W0 should be 0, W1, WD, up to WD. So we are analyzing the in-sample error function in terms of the gradient. We want to find the weight that will minimize the gradient of the in-sample error. Okay, that's our next task. So given in-sample error, the first step would be to open up the norm term here. okay, this quadratic term, which will be equivalent to the following terms. First term, which consists of W transpose X and W, and second term, and then third term. Just to demonstrate, let's consider one W case, the case where our weight is a scalar. Here it's vector, but here it's scalar. So in sample of the scalar will be, if we substitute this, then 1 over n AW squared minus ABW plus C. And the gradient of this in sample error will be equal to, we just differentiate with respect to W, will be equal to the following: 1 over n 2AW 2B. The C constant cancels out, W, okay, cancels out, this will be equal to 1, okay, 2 goes up here, 2AW. Then we are left with it. This is the gradient when we have in sample error with a scalar weight. In vector case, very similar. So in sample error is given as follows. We just need to differentiate in sample error with respect to weights, which will give us 1 over n, 2A matrix. A we denote as X transpose X, 2W, okay, transpose B, we're left with 2B, okay, all the weight will be equal to 1, and then C cancels out, that's the constant. Now, if we substitute A as X transpose X, then the gradient we obtained has the following form. This is our gradient. Here, our data, the weight, the given labels, we have this and normalize. So given the following gradient of our in-sample error for the regression problem, we want to find the weight that will minimize gradient. So for that, our task is again to find W, lean, let's denote it as lean, as an optimal linear regression weight, such that the gradient of our in-sample error function that has been derived from the square error should be equal to 0. Let me just write it down simply for convenience. X transpose X, W minus X transpose Y is equal to 0. Okay, this goes off. So we need to solve for W. It's simple. You take this to the other side, and the only thing that is left is related to X transpose X. Based on these properties of the following matrix, we can have two answers. First, if our X transpose X is invertible, then the solution is easy, and we have only one unique solution, which is obtained simply by inverting the following matrix. So W lean will be equal to the following term, and our matrix is invertible. Second, so if our matrix X transpose X is not invertible or singular, we will end up with many optimal solutions. One of the solutions will be equal to, let's say W lean will be X dagger Y, where X dagger represents the pseudo-inverse of the following entire matrix. There are many ways we can define X dagger to obtain one possible solution. So here we don't have unique solution, but multiple suboptimal solutions. So practical suggestion to solve these kind of problems is that use well implemented routines to obtain pseudo-inverse instead of obtaining the following. For numerical stability, when we have a matrix which is almost a singular, the linear regression algorithm can be summarized in 3 steps. The first step is you have your data set. You will construct your input matrix X and then output vector Y. Okay, output vector is given. Input matrix is also given. This is a supervised learning task. You put your training examples in the following tall matrix. So X1 with D plus 1 dimensionality, X2 up to Xn, each with corresponding labels. Second step involves simply inverting or calculating the pseudo-inverse, the X dagger. The W linear optimal linear regression weights will be obtained as follows, simply by matrix multiplication. This can be thought of as just one-step learning, which involves only performing matrix inversion. Just think about perceptron. Perceptron is iterative learning procedure, which involves updating weight based on the mistake on given training example, while linear regression is simple and efficient when we have the matrix that is invertible. Is linear regression a learning algorithm? Whether obtaining the weight, the optimal linear regression weight, involves some kind of learning pattern, learning behavior from the data. We can give two different answers. First, no. The W lean, obtaining W lean involves closed form, solving the closed form, or obtaining this analytic solution instantaneously. That involves matrix inverting the matrix, or approximating the pseudo-inverse of the matrix? Well, it doesn't involve iterative or sequential improving or minimization of the in-sample error, nor out-of-sample error. Second answer, however, we can say yes, we are learning from data. We have some kind of learning path. Is in-sample error good? Yes, it is even optimal, because as long as we find the matrix that is invertible, we can always find the optimal weight, which will minimize our in-sample error. How about out-of-sample error? Well, like in the perceptron case, we are dealing, yes, so as long as our in-sample error is small, as long as we are dealing with a hypothesis class with restricted VC dimension, the out-of-sample error is likely to be small enough, like in perceptron. Is it improving iteratively, the in-sample and out-of-sample error? Somehow, yes. Internal implementation of those pseudo-inverse matrix computation tools use iterative processes. So we can relate that, the calculation of the pseudo-inverse to iterative or improving iteratively. So if out-of-sample error is good, we can say that learning is happening. Let's compare the linear classification versus linear regression. In linear classification case, we were interested in estimating a hypothesis that will provide us a binary output value, which is usually plus minus 1 for binary classification tasks. And the type of the class or hypothesis we dealt with were the following in the perceptron case. H of x, we apply sign on the W transpose x. And the error function was defined as following. Basically, this is the Boolean function that gives 0 or 1, false or true, depending on the agreement between these two, predicted, given, predicted y, given y. This is a step function. It is hard to calculate or derive the gradient for this error function. Therefore, minimizing this error function involves iterative nature. It is also known as NP-hard, non-polynomial hard problem to solve to minimize this error or this kind of problem in general. While in linear regression, what we have here is y's consists of r, or real valued numbers, right? And our hypothesis class consists of, very similar to this one, h of x W transpose x. And we minimize the following squared error. And we can compare, we can say that the squared error has efficient analytic solution. In other words, the minimizing the following in-sample squared error can be done very efficiently, analytically, which involves matrix inversion again. Can we use linear regression for classification problem? As we can see here, that the y that we are interested in linear classification or belongs to the real number plus minus 1. Okay, yes, we can apply linear regression for classification tasks. First, for example, we run linear regression on binary classification data, then obtain the weight. This step is efficient, as we have seen. It involves just one-step learning, inverting the matrix. Once we have obtained those weights, we apply sign function on the obtained weight whenever we want to predict the label of the given example. So we can declare that as a G, as our classifier in perceptron. Okay. However, it is highly recommended to use linear regression for classification problems as a weight initializer. Okay, because of the nature of the error function. They try to minimize the difference between y hat and y, and ideally we want to have this to be 0. And some of the points will be too negative. Why? We are interested in just the sign of it, or too positive. So if you use linear regression or regression for classification, it's usually better to run linear regression as a weight initializer and then use perceptron-like algorithm to update the weight, which will lead to a solution much faster. Now let's take a look at the relation of two error functions. The first one is 0-1 error function that we typically use for classification tasks, which consists of the following. Alright, this is also a Boolean function. When the sign of the given hypothesis is not equal to the given or expected y or desired y, then the 0-1 error will be 1. Otherwise, 0. Okay, true or false, corresponding to 1 or 0. Well, squared error tries to minimize the following term and raise to the power of 2, okay, for the given hypothesis on the following point and desired y. If you visualize these two cases, okay, when our desired y is +1 and desired y is -1. Okay, just, because we can also use this for classification. Now let's plot the squared error and 0-1. On this axis, we have error. Here we have the weighted combination of input, okay? The value. This is inner product. And squared error tries to minimize the function, ideally obtain the following point, which corresponds to 0. Let me draw it here. So this is our positive 1 and 0. Okay, 0 is here. And we have here also the case where W transpose X is 0. Negative side, negative region, positive region, when our desired label is 1. Similarly here, we have 0 and 1. Negative region, positive region. We can see that the squared error will achieve the optimum here, while 0,1 error achieves the minimum error whenever we have the W transpose X to be positive, right, in the positive region. Similarly, for desired, when we have Y negative 1, we can see the following relation: 0,1 error and squared error. Well, by just looking at this visual graph, we can conclude that the 0,1 error will always try to achieve the perfect solution, while squared error also tries to achieve this minimum. Some of the points, some of the weight will belong to this region will be also the solution for classification problem 0,1. Therefore, we can obtain the following relationship. So if we want to apply linear regression for binary classification, we can see the following relationship. So in sample error or 0,1 error tries to achieve the 0 or minimum, and we will see the following relation. Well, in terms of out of sample error and their relationship between minimizing in sample or squared error or 0,1 error is given here. So the out of sample error considered in the VC bound is upper bounded by 0,1 error plus some model complexity term, and is bounded by regression or squared error plus some model complexity. So we can see here that provides a loser upper bound on the out of sample error. However, it is efficient, right, to calculate. We can use linear regression for classification problems again as an initializer, okay, or as initial PLA pocket vector or PLA vector, right? Today we have reviewed linear regression algorithm, the basic problem setting, and the task was to estimate the hypothesis that will approximate real values. We also have seen a linear regression algorithm that involves few steps, usually providing analytic solution with pseudo-inverse or inverting the matrix. We have briefly talked about the relationship between classification and regression if we can apply regression for classification problem. Right? Linear regression is another simple algorithm that can be used for solving simple linear regression problems. Well, in the coming lectures we will see some more examples of different algorithms, different hypothesis class that we can use in real-world examples such as logistic regression.